Welcome to the deep dive. Today we're tackling something we see every day but maybe don't fully grasp, our sun.
Right.
It's way more than just, a steady light source. It's this incredibly powerful dynamic engine.
Absolutely.
And it's shaped Earth's history. It messes with our tech right now. And, well, it holds the keys to our ultimate future.
It really does.
So our mission, as always, is to dig into the sources and pull out the absolute key insights for you. A shortcut to getting genuinely clued in on the sun's, frankly, sometimes startling power.
And I think fundamentally we need to remember what it is. It's this enormous ball of superheated plasma.
Plasma, right.
Mostly hydrogen, maybe 73%, and helium, about 25%. And it's huge, 99.86% of everything in the solar system, all powered by nuclear fusion.
99.86%.
Yeah, it's staggering. But the key thing, what's fascinating here, is that this thing that looks so constant is actually incredibly dynamic, constantly changing, constantly helping us.
Dynamic is the perfect word. Because it's not just light and heat, is it? There's this whole other side, this space weather.
Exactly. Solar flares, CMEs, coronal mass ejections, the solar wind.
Okay, hold on. Let's unpack those. What is space weather, really? And, how does the sun actually do that? Why should we be paying attention?
Good questions. Okay, so solar flares. Think of them as sudden, really intense bursts of energy. Charged particles, magnetic fields, a roughing from the sun's outer layer, the corona.
Which is already incredibly hot, right?
Oh, incredibly. Millions of degrees Fahrenheit normally. But during a flare, it can shoot up to tens of millions of degrees.
Wow.
Then you have CMEs, coronal mass ejections. These are massive clouds of plasma, basically ionized gas that get thrown out from the sun.
Thrown out, like, towards us?
Sometimes, yeah. Directly towards Earth. It's happened. In fact, the first time anyone recorded one was way back in 1860 during an eclipse.
Huh. I didn't know that.
And finally, the solar wind. This is more of a constant thing. A continuous stream of charged particles, mostly protons and electrons.
Where does that come from?
It flows out from things like coronal holes, active regions on the sun, and it's fast, about 1,000,000 miles per hour by the time it reaches Earth.
1,000,000 miles per hour. Constantly.
Pretty much. The idea was actually theorized back in '57 by Eugene Parker. He figured it out by looking at comet tails.
Ah, makes sense.
And then NASA's Mariner 2 probe confirmed it in '62. So yeah, it's this constant stream.
It's amazing how much is just pouring off the sun all the time, unseen. And it's not totally random, is it? There's that cycle.
The 11-year solar cycle, exactly. You
Yeah.
see it in the number of sunspots, those cooler, darker patches where the magnetic fields are really intense.
They come and go over 11 years.
They wax and wane, yeah.
Yeah.
And the really mind-blowing part, at the peak, or rather the end of each cycle, the sun's entire magnetic field flips. North becomes south, south becomes north.
The whole thing just reverses polarity.
The whole thing. A massive cosmic reset. It reshapes the entire magnetic environment out there. Okay, that's the sun now. But let's jump back. Way back. Our sources bring up something pretty dramatic, this idea that a massive solar event, an SPE,
A solar proton event, yeah.
might have actually triggered the Pleistocene mass extinction.
It's a fascinating hypothesis. And there's some compelling evidence behind it, not just guesswork.
What kind of evidence are we talking about?
Well, researchers found this really sharp spike in carbon-14 in the atmosphere. It dates to almost exactly 12,837 years ago,
How do they know that precisely?
from something called the Cariaco Basin Varve record. Think of it like tree rings, but in sediment layers on the seabed. Each layer is a year. Super precise.
Okay, so a carbon-14 spike.
An immense spike. They think it was caused by a solar proton event way, way bigger than anything we've measured recently, maybe 125 times the radiation fluence of a big one back in 1956.
125 times. What does that mean for Earth?
It means it could have delivered a lethal dose of radiation. We're talking 3 to 6 sieverts, maybe more, hitting the surface.
Lethal. To large animals, certainly. They propose it as a major factor in wiping out the Pleistocene megafauna mammoths, saber-toothed cats, that sort of thing. And maybe even smaller mammals and birds, too.
Wow. So the sun as an extinction trigger.
And there's more.
Yeah.
That exact time period, it lines up perfectly with a huge acidity spike found deep in Greenland ice cores.
Ice cores, like layers of frozen history.
Exactly. Trapped bubbles, chemical layers. This specific layer also shows high nitrate levels and a jump in beryllium-10.
Beryllium-10. What's that tell us?
Beryllium-10 is created when high-energy cosmic rays smack into our atmosphere. So a spike means a big influx of cosmic rays, like from a massive SPE.
Okay, so the radiocarbon, the ice core acidity, the beryllium-10, it all points to this massive radiation event.
It paints a pretty consistent picture, yeah? They even found evidence that suggests the ozone layer over the poles might have been temporarily destroyed by the radiation, letting in intense UV.
And that links to other things found around that time.
Yes, it correlates with an abrupt climate shift and also signs of global wildfires, indicated by ammonium ions in the ice. It all seems to cluster around that 12,837-year mark.
That's incredible. You know, what's interesting is, unlike, say, a single comet impact, this solar idea, it could allow for multiple events, right?
That's a really key point. Other carbon-14 spurts have been found in ancient records, suggesting maybe it wasn't just one big zap, but potentially several hazardous solar events over time.
Which fits the extinction pattern maybe better.
It's definitely compatible. But the scale of that main event, the 12,837 one, it's hard to overstate. 125 times the 1956 event's fluence. And if the Earth's magnetic shield, the magnetosphere, buckled under the associated solar storm,
Then the radiation dose would be even higher.
potentially over 6 sieverts. Truly catastrophic levels. It's a stark reminder of the sun's raw power.
Absolutely sobering. Okay, so that's the ancient past. But this isn't just history, right? Space weather is happening now. How does this constant solar activity affect us today with all our technology?
Oh, it has a huge impact, often in ways people don't realize. Satellites are a prime example. They are incredibly vulnerable up there.
How so?
Well, those charged particles we talked about, they can cause all sorts of problems. False commands, damaged electronics.
Like phantom signals telling the satellite to do something?
Exactly.
Yeah.
Or they can cause electrical charging on the surface or even deep inside the satellite's components. This can lead to electrostatic discharges, basically, sparks that can damage or destroy sensitive parts. We saw big anomalies linked to this back in January '94, for instance. Sometimes you just lose control, or the whole satellite fails.
Okay, that's worrying for our communication and GPS.
Definitely GPS, and also power grids. This is a big one.
Power grids. How does the sun affect power lines?
When a really strong blast from the sun, like a fast CME or solar wind gust, hits Earth's magnetic field, it compresses and shakes it.
Right.
That rapid change in the magnetic field induces electric currents in the ground. We call them telluric currents. And because power lines are long conductors, these currents flow into the grid. They can overload transformers, trip circuits.
Leading to blackouts.
Widespread blackouts, potentially. It's a major concern for grid operators.
Any other systems?
Oh, yeah. Radio communications, especially high-frequency HF radio, the kind used for long distance, like transoceanic flights. Solar storms mess with the ionosphere, making it harder for those signals to bounce.
So flights could lose contact.
It can happen, yeah, particularly near the poles. GPS navigation can also get degraded or interrupted. And think about astronauts. They're outside the main protection of the atmosphere. Solar radiation is a serious health risk for them.
On the ISS or future Mars missions?
Exactly. Even pipelines aren't immune. Those telluric currents can flow through long metal pipes, causing voltage swings that speed up corrosion.
So it literally shortens the lifespan of critical infrastructure.
It can, yeah. It's surprisingly far-reaching.
You know, there's that story from the Cold War, May 1967. It sounds like something from a movie.
Ah, yes, the missile warning system incident.
Tell us about that. A solar flare almost triggered.
It was incredibly tense. A powerful solar flare erupted, and it completely jammed the radar systems of the U.S. Air Force's ballistic missile early warning system. All 3 sites went down.
And back then, radar jamming
was seen as a potential act of war, a prelude to a Soviet missile attack. Things escalated very quickly.
But it wasn't the Soviets.
No. Luckily, the U.S. had recently started monitoring solar activity. Someone connected the dots just in time, realized it was the sun, not an attack.
Wow. So solar science literally prevented a potential nuclear exchange.
It certainly seems that way.
Yeah.
It underscores how critical understanding and predicting space weather is, even for national security.
Which leads perfectly to, how do we predict this stuff now? Are we getting better?
We are, actually. There have been some really exciting developments, especially using AI. NASA and IBM recently unveiled a model called Surya.
Surya, like the Hindu sun god.
Exactly. It's been trained on, I think, over 9 years of data from the Solar Dynamics Observatory, SDO.
And what does it do?
It analyzes images and data from the sun, looking for the subtle early signs of flares and eruptions before they happen.
So it gives us more warning.
That's the goal. Early results are really promising. They think Surya can provide forecasts maybe up to 2 hours in advance, and with something like a 15% improvement in accuracy over older methods.
2 hours doesn't sound like much, but I guess in space.
It's critical. An extra hour or two. That's enough time for satellite operators to put spacecraft into a safe mode. for power grid managers to adjust loads and protect transformers, for airlines to reroute flights, or for astronauts to take shelter.
That makes a huge difference.
It really does. And NASA's making the model open source, so everyone can benefit and contribute. It's a big step for global space weather defense.
Okay, so we've covered the sun's power in the past, its effects now, and how we're trying to predict it. Let's shift focus way out, the really long term. What's the sun's ultimate fate, and what does that mean for Earth?
Well, our sun's a middle-aged star, you could say.
Mm.
A G-type main sequence star. It formed about 4.6 billion years ago.
And it's got about how long left in its current state?
Roughly another 5 billion years of relative stability. But relative is the key word.
Uh-oh. Meaning?
Even while it's stable, it's slowly getting brighter. About 1% brighter every 100 million years.
That doesn't sound like much.
Over cosmic timescales, it adds up. Somewhere between, say, 700 million and 1.5 billion years from now, that gradual brightening will make Earth's surface too hot for liquid water.
So, boiling oceans. End of life as we know it.
Pretty much.
Oh.
Long before the sun itself undergoes its major transformation, Earth likely becomes sterile.
Okay. And then comes the big change.
Then comes the big change. In about 4 to 7 billion years, the hydrogen fuel in the sun's core starts to run low. Fusion slows down there, but starts in a shell around the core.
And that makes it
Expand dramatically. The outer layers will swell outwards, turning the sun into a red giant. It could become more than 200 times its current size.
200 times. What happens to the inner planets?
Mercury and Venus will definitely be engulfed, swallowed by the expanding sun.
And Earth, are we far enough away?
It's complicated. As the sun expands, it actually loses mass, which should make Earth's orbit drift outward slightly.
No. So maybe we escape.
Maybe initially. But the sun's outer layers, the chromosphere, will be much closer. Tidal forces and drag from that thin atmosphere will likely slow Earth down.
And pull us in.
That's the current thinking, yeah. Earth's orbit will decay, and our planet will eventually spiral into the sun and be engulfed. Probably around 7.6 billion years from now.
So Earth gets eaten by the sun.
Seems likely. It won't be a supernova, though. Our sun isn't massive enough for that kind of explosion.
Right, you need much bigger stars for supernovae or black holes.
Exactly. Instead, after the red giant phase, the sun will shed its outer layers, creating what we see as a planetary nebula, often beautiful structures.
And what's left behind?
A very hot, very dense core, about the size of Earth, actually. A white dwarf.
Just a remnant core.
Right. It'll just sit there and cool down over billions, trillions of years, eventually becoming a cold, dark black dwarf, not radiating anything.
Wow. That's quite the final chapter. Puts our daily worries in perspective, doesn't it?
It certainly does. We're talking time scales that are hard to even comprehend.
But, humans, we always think about, could we do something? Even facing something that immense and far off. The sources mention some wild ideas.
They did. Theoretical, of course, but fascinating. The idea of actually moving Earth.
Moving the planet? How?
Well, maybe using gravity tractors, massive objects placed strategically to gently nudge Earth's orbit over millions of years. Or perhaps redirecting asteroids to fly by Earth in just the right way to give it a gravitational boost.
Tiny adjustments over vast time.
Exactly. A 1% orbital shift every 100 million years might be enough to keep pace with the sun's brightening, at least for a while.
Or maybe block the sunlight, like a giant umbrella.
That's another concept, deploying huge reflective shields in orbit, or maybe a massive sunshade positioned at the L1 Lagrange point, a stable spot between Earth and Sun.
Could we do that technologically?
The sunshade is a huge engineering challenge, but maybe not impossible in the far future. A simpler, though perhaps messier, idea is atmospheric seeding.
Like geoengineering?
Sort of. Pumping something like sulfur dioxide, SO2, into the upper atmosphere to reflect more sunlight away. We could probably do that with current tech, though the side effects would need serious consideration.
And if Earth just becomes truly uninhabitable?
Then the long-term strategy becomes leaving, colonizing other places in the solar system, maybe the moons of Jupiter or Saturn, which might become more temperate as the sun heats up.
Escape pods on a planetary scale.
In a manner of speaking, yes. Human ingenuity against cosmic destiny.
It's incredible how we've pieced all this together, isn't it? From ancient sun worship and early calendars
To Galileo pointing his telescope and seeing sunspots for the first time.
to now having spacecraft practically touching the sun. How do we study our star today? What are the key tools?
We have an amazing fleet of space observatories now, ESO of the Solar and Heliospheric Observatory has been a workhorse for over 25 years.
What has ESO shown us?
Oh, so much. It revolutionized space weather forecasting, helped us see the structure inside sunspots, measured how the solar wind accelerates, discovered things like coronal waves and solar tornadoes.
Yeah.
It even found over 1,000 comets.
Wow. And SDO.
The Solar Dynamics Observatory, launched in 2010, SDO gives us these incredibly detailed, high-resolution views, especially in wavelengths we can't see from Earth, like extreme ultraviolet. It's shown us material streaming off sunspots like never before.
And then there are the daredevils. Parker Solar Probe.
Absolutely. Parker is just, well, audacious. Named after Eugene Parker, who theorized the solar wind, it flies closer to the sun than anything ever built.
How close?
It dives right into the corona, the sun's atmosphere, just 4 million miles from the surface at its closest approach.
How does it survive that? The heat must be incredible.
It is. Temperatures outside the probe can reach up to 3 million degrees Fahrenheit. It has this cutting-edge heat shield made of carbon composite that protects the instruments.
And what's it measuring in there?
It's measuring things directly, tasting the solar wind, sampling energetic particles, understanding the energy flow right where it all originates. It's in situ measurement.
And Solar Orbiter is doing something different.
Right. Solar Orbiter, launched more recently in 2020, is more about taking pictures. It carries advanced cameras and telescopes to get the closest ever images of the sun's surface.
Finding new things.
Definitely. It's already revealed these things called campfires. Tiny, previously unseen flares all over the sun. What's fascinating is how they work together.
Parker and Solar Orbiter.
Yeah, Parker dives in and takes direct measurements, while Solar Orbiter hangs back a bit and takes detailed pictures. Combining those two perspectives is pushing our understanding forward incredibly fast.
What an amazing journey, from potential ancient killer to Cold War near miss to modern tech nuisance, and finally the ultimate arbiter of Earth's fate. The sun really governs everything.
It truly does. It might look like a friendly, familiar face in the sky, but it's a complex, active star. Its constant activity means we absolutely have to keep studying it, keep monitoring it. It's not just curiosity.
It's survival.
Both now, protecting our technology and astronauts, and thinking about the very, very long-term future of life on Earth.
Exactly. So for you, our listener, here's something to really ponder. Given this dual nature of the sun giver of life, potential taker of life, and these immense timescales, what's our responsibility as a species? To understand it, maybe mitigate its effects, adapt to its changes, not just for us, but for everything else on this planet.